Hello, my name's Jeff Messier. I'm a professor of electrical and computer engineering in the Schulich School of Engineering at the University of Calgary. And this is Module 12 in our Circuits 2 Electronics lecture series, where I'm going to talk about op-amps. Now, technically, I guess op-amps for most of you will be review, right? Most Circuits 1 courses do introduce op-amps. In particular, they'll introduce what we'll refer to as the ideal op-amp. And this is a drawing of an op-amp. So we typically draw it as a triangle. It's got two input terminals, the positive and negative terminal. It has some output voltage, VO, and the voltage applied to the negative terminal I'm going to call V1. The voltage applied to the positive terminal I'm going to call V2. And then we have potentially some current going into the positive terminal, I2, and some current going into the negative terminal, which is I1. And you would have learned to analyze basic amplifier structures using this op-amp. And the analysis of those structures would be based on a set of sort of assumptions and rules that you can make. And so what I want to do is I want to start there, just do kind of a review of the ideal op-amp analysis. And I'm going to give you those assumptions that we always use when performing this analysis. But then I'm going to ask a few questions about where these assumptions come from, because this was a topic I know when I was an undergraduate student, I was never fully satisfied with how op-amps were explained, and even in a lot of circuits textbooks, they kind of sweep a lot of stuff under the rug. So I'm going to spend a little bit of time in this module talking about where some of these assumptions come from. And so let's start out with the equation for the output voltage. So the output voltage, and you might have seen this equation, is equal to some gain factor A times the difference between the voltages applied at the input terminals. And often when you read in textbooks, we say that this gain value A is very, very large. Ideally, it would be infinite, which I kind of always had a little bit of trouble with, because if it was infinite, then the voltage would be infinite, as output voltage would be infinite as well. But that's what we often assume. We also assume that the input impedance of the op-amp is infinite, so that our currents going into the input terminals I1 and I2 are equal to 0. And that one I had a little bit of an easier time with, because you can, using FET transistors and things like that, create circuits that do, in fact, have a very high input impedance. So that one's not too bad. And usually when we perform analysis of an op-amp amplifier, we don't just sort of look at the device itself. We connect the device into some kind of resistor network that usually involves some sort of feedback, where we connect the output to one of the input terminals through, again, a resistor, a network of resistors. And so I'll do that example where we use a resistor network to create a non-inverting amplifier using an op-amp. Okay, so here is the non-inverting amplifier. And again, you might remember circuits that sort of look like this. And our objective is to calculate the voltage gain. And the voltage gain, just like for the dependent voltage source in the previous module, I'm going to define the voltage gain G as the ratio of the output voltage divided by the input voltage. And so the output voltage is just the output of the op-amp relative to ground, and the input voltage is the voltage applied to the positive terminal relative to ground, and this is just this independent voltage source representing the input. And so when performing this analysis, crucially, we assume that the voltage at the input, the input voltage at the negative terminal, V1, is equal to the input voltage at the positive terminal, V2. And I'm going to loop back on this assumption in a second, but probably you've used this assumption before, and so let's use it again. So what I want to do is calculate V1, and so V1 is the voltage at this node. V1 is just equal to, if we look at the output voltage is at this node, and then we have two resistors in series connecting our output voltage to ground. No current flows into this terminal, so all the current flows through these two resistors to ground. And so the voltage at V1 is just given by the voltage divider law. So it's the voltage across resistor 1 divided by the sum of resistor 1 and 2 multiplied by the output voltage, which is the voltage at that node. And we know that that V1 is also equal to V2. And in this particular circuit, V2, which is the voltage at that node, is just equal to our input voltage, Vi. And so we have our input voltage being equal to R1 over R1 plus R2 times the output voltage. And so it's relatively straightforward to calculate our voltage gain. G is equal to output divided by input. And if we sort of manipulate this resistance ratio, we can express this as, well, I guess R1 over plus R2 over R1, or more commonly you see it expressed as 1 over R2 over R1. And so that's our voltage gain, right? So our voltage gain is at least 1. And if we choose a resistance value that's larger than, much larger than, or resistance value for R2 that's much larger than R1, then our gain just goes up. And so we've created an amplifier, and, kind of away we go. But, I'll loop back to here because this is the one that I always had trouble with. So the voltage is equal at these two terminals. Well, I always had a hard time with this assumption and this equation here. So if, so here are kind of my questions. So if V1 and V2 are equal, then isn't our output voltage equal to 0, right? Because we've got some gain, V2 minus V1. But if these two are the same, then shouldn't this be 0? And, how do we, why are these the same? So I guess if we wanted V1 and V2 to be the same, one way to design our circuit would just be to short circuit these two terminals together inside the amplifier, and then the voltages would always be forced to be the same. But then we couldn't have infinite input impedance because these would be shorted together. So probably, maybe you've asked this question yourself, and perhaps you've been told, kind of as I was told, well, it has to do with this infinite resistance. So if this difference is almost zero and this is almost infinite, then somehow they balance out, which, okay, that's fine, but it still doesn't tell us why we assume this. Like, is there something special inside the op-amp that somehow drives these two voltages together? And it turns out the answer is actually no. So the reason why we make this assumption, V1 is equal to V2, it's not because of some specially internally designed mechanism inside the op-amp. It's actually a function of this feedback network of resistors. And without connecting the output to the input somehow, this assumption is never ever true. And so what I want to do next is I want to sort of delve into this a little bit more, talk about this feedback network, analyze it in a little bit more detail. And by the time we're finished, you'll see where these assumptions come from. Okay, so before we can look at feedback, or before we look at feedback, I do want to talk a little bit about the model that we assume for a non-ideal op-amp. And so what I want to do is I want to dive inside that little triangle and see what's inside of it, basically. So on the left-hand side, we've got our traditional op-amp symbol. And then on the right-hand side, I've drawn a circuit that contains a dependent voltage source. And this circuit is meant to represent what goes on inside an op-amp. And so just so we can map kind of our terminals, if terminal or nodes 1 and 2 here represent the positive and negative terminals, then that would correspond to these 2 points. And then if our output is node 3, that corresponds to this node in our voltage dependent, or in our dependent voltage source diagram. And so we represent the connection, like the internal connection between our two input terminals using a resistance RD. The voltage across these two terminals I'm going to refer to as VD, that's the differential voltage. The voltage generated by our dependent source is equal to A multiplied by VD. And we have a resistance in series with our dependent source, RO. And so what I want to do is compare what we would assume for this circuit design if we had an ideal op-amp versus what we get with an actual op-amp. And the op-amp that I've chosen for comparison is the TLV411X, and then X is 1, 2, 3, or 4. And depending on what you choose for X, you get a different number of op-amps in your integrated circuit package and a few different power options and stuff like that. So ideally, we assume that the input impedance for an op-amp is infinite and that no current can flow into the positive or negative terminals. That's achieved if we assume that this differential resistance, RD, has an infinite value. And so, is that true in practice? Well, if you look at the TLV411 datasheet, this differential resistance has a value of 1,000 gigaohms. So yeah, it is really pretty big. And for most practical circuits, we can assume that it's infinite. What about this output resistance RO? In a normal ideal op-amp, we assume that the full value of our dependent voltage source is applied across the output terminals, which basically means we assume our output resistance is 0. In the TLV411 datasheet, this is approximately equal to 5 ohms, and it does vary depending on the frequency of oscillation of the input signal. And 5 ohms, depending on your application, cannot be neglected. So for example, if you're using your op-amp to drive a speaker, then the resistance of your load is probably in the neighborhood of 8 ohms typically, maybe as low as 4 ohms. And as soon as your load resistance is on the order of your output resistance of your source, you can't neglect it anymore. Now, fortunately for max power transfer, the load resistance would have to be the same as this output resistance, and it's pretty close already. So if you're using this to drive a speaker, you're probably in reasonable shape. Finally, what about this gain? Well, we said on the previous page that we typically assume that this gain is infinite. Is it really? In the datasheet, this is about 100 dB. So that's 10 billion in linear terms. And that's pretty high, right? That's a very significant amount of gain. Not infinite, but still a really, really big number. So that's kind of how we stack up. Also, we have to take into account the limitations that exist on the levels of output voltage that our op-amp can actually generate. So let's assume that our positive and negative power supply voltages that we apply to that we give to our op-amp integrated circuit are represented by VDD and VSS. So if I was to create a graph or a plot where the x-axis was that differential voltage and the y-axis was our output voltage, ideally we would expect this to be a straight line because we know that our output voltage, VO, is equal to some constant times VD, and that's the equation for a straight line, right? So we would just, our output voltage would look like that. And the slope of our line would be equal to A. However, we have a maximum positive power supply level of VDD and a maximum negative power supply level of VSS. And so if we're only giving our integrated circuit a voltage of VDD, we can't expect it to generate an output voltage that's any higher than that. And so we would, once we get to this point, we would expect our voltage to sort of clip and flatten out at the source voltage. And in fact, it's even a little bit worse than this, because if you look in the datasheet, we have voltage levels VOH and VOL that are a little bit offset from our supply levels, offset by a couple hundred millivolts. And it's these VOH and VOL levels that define the maximum positive and negative values that we can generate with our op-amp. And so you have to design your circuit to make sure that your maximum output voltages that you expect fall within this range. As soon as you try to generate output voltages that exceed this range, then you're just going to clip and you're going to get noise in your circuit, basically. So those are a few practical op-amp things to keep in mind. And again, one of the reasons why I wanted to show you this non-ideal op-amp model is to reinforce again this assumption that we made at the start of our discussion that the voltage on our positive terminal and our negative terminal have to be the same, right? This is fundamental to our analysis of op-amps. But if we sort of dive inside our op-amp, we can see that there's nothing here that would enforce that. In fact, we've got just a really big resistor separating these two terminals. And so it's perfectly possible that we might have, a very large difference in the voltage across those two terminals. So again, there's nothing sort of sneaky hiding inside the op-amp that causes us to make this assumption. This assumption, as we're going to see next, is a function of the feedback network that we hook up around the outside of the op-amp. Okay, so here is a general feedback network connected to our op amp. And we're now going to analyze this network without the V1 equals V2 assumption. Oops. Let me draw that in there. So let's take a look at our circuit. We've got our positive and negative op amp terminals. We've got our input voltage connected up directly to the positive terminal. This is going to turn into the non-inverting op amp, so that's where we're going with this. But rather than having the resistor network that we normally have with the non-inverting op amp, or the non-inverting op amp amplifier, I'm just going to have a box B, or a box here with a factor beta inside it. And the voltage at the negative terminal, V1, is equal to beta times the output voltage. And typically, beta is less than or equal to 1. So if we directly connected the output voltage to the negative terminal, beta would be equal to 1. And if we add resistors in here, like we do with the non-inverting amplifier, then beta is less than 1. Right? So we attenuate our output signal. We know that our differential voltage is equal to the input voltage minus V1. Right? So that's the differential voltage between these 2 points. And we know that the output is equal to A times the differential voltage. And we're not, for this analysis, making the V1 equals V2 assumption. And so what I want to do though, like the objective of our analysis is still the same. I still want to figure out the voltage gain of this kind of op-amp feedback structure. I want to figure out how the size of our output voltage relative to our input voltage. So this is our objective, just like it was at the start of our discussion, except we're not going to make the same assumptions. And so to start off with, we know that the output voltage is A times the differential voltage, and that's just equal to the input voltage minus V1. We know that V1 is an attenuated version of the output voltage. Actually, I'll write this down here. So we've got A times the input voltage minus an attenuated version of the output voltage. And what we're trying to solve for is the ratio of the output voltage to the input voltage. And kind of the same, similar to what we were doing with the voltage transfer functions for our Laplace analysis, I want to get this equation just in terms of VO and VI, and I've done it. So output voltage, input voltage, this was V1, but we know V1 is an attenuated version of the output voltage. And so now I can write this as AVI minus A beta VO. And if I now take the ratio of V out over V in using this equation, I find that G is equal to A over 1 plus beta times A, or putting in a slightly different form, and you'll see why I do this in a second, I'm going to take a factor of 1 over beta out front. And if I've got 1 over beta, then I have to add a beta up into that numerator. So I have A times beta over 1 plus A times beta. And so this is the gain of our circuit. And for the first time, unlike the analysis that we did to start off this module, we have the attenuation due to the resistor network that's going to connect our output voltage to our input voltage. But we've also accounted for this almost infinite gain factor A, right? We assume this is normally infinite. It's actually 100 dB, which is 10 billion, right, for the op amp that we considered on the previous sheet of notes. But it's a very large number. And so now let's expand on this. So let's let T represent the product of A and beta. And let's call this our loop gain. So this is known as our loop gain. Why do we call it the loop gain? Well, let's imagine we're sort of going around a loop, our feedback loop. So we go through the amplifier, we get amplified by A, and then we go through our feedback loop and we get attenuated a little bit by beta. And so that's why we called it our loop gain. And so we know that if we express this expression in terms of T, we know that G is equal to 1 over beta T over 1 plus T. Now, T is usually really, really large. Yes, beta is less than 1, but it's not usually super, it's not usually super, super tiny. It might be equal to a third or a fifth or something like that. And A is equal to 10 billion, right? So our loop gain is still very, very large. And because T is large, T is approximately equal to 1 plus T. And so our loop gain is approximately equal to our voltage gain, the ratio of the output voltage to the input voltage, is approximately equal to 1 over beta. In fact, our ideal loop gain is 1 over beta. So it's not infinite, right? So this infinite gain has kind of disappeared. And in return, the gain of our amplifier is 1 over beta. And because beta is always less than or equal to 1, the voltage gain of our overall amplifier, output over input, is going to be greater than 1. So we get some amplification, but not an infinite amount of amplification. Now, what about the assumption that the voltage on these two terminals is equal? It turns out that the feedback network makes this differential voltage quite small. Not zero, but really quite small. And so we know that our differential voltage VD is equal to our input voltage minus the voltage at V1. We know that this is an attenuated version. Whoops. Hopefully I can fit it all in here. An attenuated version of the output voltage. And we also know now that our output voltage is equal to 1 over beta times T over 1 plus T times our input voltage, right? Because that's just our expression for gain. So if we substitute this in, we have input voltage minus beta, and the 1 over beta will cancel. So we get T over 1 plus T times VI. But for very large values of loop gain, and T typically is very large, this quantity is approximately equal to 1, which means the difference between the two is approximately equal to 0. It's not exactly 0, and we're going to do an example now with real numbers from a real op-amp to sort of show you, but this is where the V1 equals V2, or sorry, the V1 equals V2 assumption comes from. It's the feedback. What's going on here? Well, basically, this feedback network is, the very large gain of the op-amp is causing the output voltage through the feedback network to make sure that V1 tracks the input voltage very, very closely. So you can imagine the output voltage is changing and going through this feedback network so that it's trying to keep, so that V1 is as close to the input voltage as possible. So it's thanks to this feedback that the voltage at this terminal is tracking our input so closely, as we can see from the equation down here. So let's plug in some real numbers and see how this all hangs together for the non-inverting amplifier. So we'll kind of close the loop, I guess, because this module is all about feedback. We'll close the loop and we'll redo the non-inverting amplifier that we started the module with using these assumptions. Okay, so here is the non-inverting amplifier using the sort of this feedback analysis that we've developed. So the first thing to note is that I've replaced this sort of box with that beta factor by a voltage divider, a couple of resistances R1 and R2. Now, this voltage divider is basically exactly equivalent to the resistance network that we had hooked up to our non-inverting amplifier at the very start of this module. And so if that's not clear, you must convince yourself of that before going any further. So write this diagram down, pause the video, rewind it to the start, look at the non-inverting amplifier, and convince yourself that this circuit is exactly the same as the one that we started at or analyzed at the start of the module. So assuming that you're now comfortable with that, the voltage at V1, just using the voltage divider equation, V1 is equal to R1 over R1 plus R2 times the output voltage. That's just the voltage divider formula. We know from our feedback analysis, when this used to just be equal to beta, in our earlier equations, we said that V1 is equal to beta times V naught, and beta is less than or equal to 1. And so in this case, this beta factor is just equal to R1 over R1 plus R2. And that's really important. So this beta, it's not some kind of mysterious floating factor that can't be understood. It is just the attenuation of these resistances in our feedback network. So again, pause, think about that, and make sure you're comfortable with that idea before we move on. If you're assuming that you're okay with that now, we can start to use some of the equations that we developed on the just a moment ago. So we know that our ideal voltage gain, output voltage over input voltage, is equal to 1 over beta. Beta is equal to R1 over R1 plus R2, R2 over R1. So we can write it like that. Exactly the same as our ideal sort of circuits 1 type analysis of this amplifier at the start of this module. What about the non-ideal voltage gain, right? So we know that the actual voltage gain is equal to 1 over beta times our loop gain divided by 1 plus our loop gain. And so what is this loop gain? Well, let's assume that A is equal to 100,000, which would not be a very good op amp. Normally they're even better than that, but let's say A is equal to 100,000. And let's assume that R1 and R2 are both equal to 1 kilo ohm. That means that beta is equal to 1/2. And so our ideal gain is equal to 1 over beta, which is equal to 2. And that's the same thing that we get if we do R2 over R1. Because this ratio would be equal to 1 because those resistances are equal. So the 1 over beta thing holds together. The actual gain is 1 over beta. Actually, I'll just write it in. 1 over beta, which is equal to 2, times T, which is 1/2, which is the beta, times 100,000, 1 plus 1/2 times 100,000. So that's equal to 1.99996. So basically 2. So even for quite a poor op amp, a linear gain of only 100,000, we get an actual gain that's extremely close to the gain predicted by the ideal equation. And finally, let's take a look at our differential voltage. For an input voltage of 1 volt. So our differential voltage is equal to 1 minus T over 1 plus T times 1. And if we plug in the value for T, we get a value here of 20 microvolts. And so very small, right? Quite small compared to the 1 volt input. So you can see where this V1 equals V2 assumption comes from, but it's not 0. 20 microvolts is certainly very measurable. There are lots of electrical engineering circuits, particularly communication receivers and low noise instrumentation type circuits, that can measure voltages that are much smaller than 20 microvolts. And so it's approximately 0. Obviously things hold together. The analysis that we perform for the V1 is equal to V2 assumption gives us the proper gain. However, now hopefully having gone through this module, you can kind of see where all of this comes from. By all means, continue to use the V1 equals V2 approximation. It's super, super handy. But now hopefully you have an idea of where it comes from and how these sort of properties of the op amp kind of all work together to make the assumption hopefully make sense to you.